A bullet traveling forward in a perfectly straight line possesses a strict, indestructible physical quantity, translational momentum. Contrast that with a rapidly spinning industrial flywheel. It is massive and entirely full of kinetic energy, but it is moving absolutely nowhere. A linear impulse of force over time transforms into a conserved quantity of mass times velocity, or mv. But apply these linear vectors to a spinning wheel, and you encounter a mathematical problem. The outward vectors perfectly cancel each other out to zero. Momentum functions as the universe's geometric accounting system, tracking the persistence of motion through straight lines and spinning arcs alike. To track these complex interactions, we have to uncover the hidden accounting that keeps the total quantity of motion constant, regardless of the system's shape. We establish the baseline rules of one-dimensional linear motion by looking at a nearly frictionless environment. This overhead diagram visualizes momentum as a vector, meaning direction directly dictates the math. If two identical pucks move toward each other at the exact same speed, one carries a momentum of positive mv and the other carries negative mv. If they hit dead-on and stick together in an inelastic collision, they stop completely. Their total combined momentum of the system, positive mv plus negative mv, remains exactly zero. If the collision is perfectly elastic, they bounce with perfect springiness. They swap their positive and negative mv values entirely, but the total sum across the system is still zero. We can stress test this rule by looking at a single billiard ball hitting a table's rail and bouncing straight back. The ball approaches with a momentum of positive mv and rebounds with negative mv. On paper, that registers as a massive, sudden change in the system's total momentum. Zooming out, this diagram resolves the discrepancy by expanding the system boundary. The billiard table is anchored by friction to the Earth. When the ball reverses direction, the entire mass of the planet recoils, absorbing the change by gaining an infinitesimally small vector in the opposite direction. Gravity enforces this exact same dynamic. As an object falls and gains downward momentum, the Earth gains an equal upward momentum to meet it, keeping their combined vectors perfectly balanced at zero at every instant. Whenever momentum shifts, the universe strictly balances the ledger, even if it requires moving a planet to do so. Motion is never created from nothing. This absolute mathematical balance holds true even for complex systems that violently break apart mid-flight, like a high-velocity artillery shell. This 3D diagram tracks the shell's center of mass, the mathematical average point of the body. The object behaves as if all its mass is concentrated precisely at this single dot, tracing a smooth, predictable parabolic arc. If the shell explodes in midair, extreme internal chemical forces propel matter outward in chaos. As this animation maps out, Newton's third law demands a strict accounting for that chaos. Every single fragment hurled outward by the explosion is paired with another fragment hurled in the exact opposite direction. Because these internal actions and reactions cancel each other out perfectly, the vector sum of all the internal movements is absolutely zero. The physical structure of the object is destroyed, but its mathematical center remains utterly unaffected, continuing along the exact same arc. Internal forces can wildly alter a system's shape and distribute its parts, but they never alter the trajectory or total momentum of the system. Rotational motion presents a unique mathematical challenge. A spinning wheel's center of mass is completely stationary, meaning the linear rules we just established seem to break down. Measuring linear velocity, or v, is useless here. The rim moves rapidly, while the center doesn't move at all. This diagram introduces angular velocity, represented by the Greek letter omega. Instead of measuring distance in a straight line, it measures the sweep of an angle over time, a value that applies uniformly to every single part of the turning object. We can bridge linear force to this rotational movement by stripping the system down to a single point mass on a rigid, massless arm. We start the derivation with Newton's second law for linear motion. Force equals mass times linear acceleration, or F equals ma. We then substitute linear acceleration with its geometric equivalent, the radius multiplied by angular acceleration, giving us F equals mr alpha. A rotational force is called torque, defined as force applied at a distance from the center. By multiplying both sides of our equation by the radius, we convert the entire system to torque, resulting in the equation tau equals mr squared alpha. By isolating the quantity mr squared, we define the moment of inertia, I. This is rotational motion's exact equivalent to linear mass. Converting linear algebra into circular geometry reveals an object's rotational resistance is defined by the precise location of its mass relative to the axis. The inclusion of the radius squared, r squared, has profound mechanical consequences. You can drastically change an object's physical resistance without ever changing its mass. This 3D model visualizes a solid sphere made of 1,000 equal subunits of mass. Its moment of inertia is the average of all their individual distances from the central axis. If we rearrange those exact same 1,000 subunits into a hollow shell, the total mass remains perfectly identical, but the average radius has drastically increased. Because that distance is squared, this hollow sphere now has a massively larger moment of inertia. It requires significantly more torque to stop. Engineers apply this exact geometric principle to stabilize machinery. Gyroscopes and flywheels are built with extremely heavy outer rims and completely hollow interiors to maximize this resistance. This leads directly to the conservation law for rotational mechanics. The total angular momentum of an isolated system, its moment of inertia multiplied by its angular velocity, must remain absolutely constant. We see this balance calculated in real time by a figure skater spinning rapidly on the ice with heavy weights extended outward. When the skater drops their arms to their sides, they pull mass closer to the axis. This physical retraction drastically shrinks their moment of inertia. This top-down diagram demonstrates the mathematical compensation. To keep the total angular momentum completely constant as the moment of inertia drops, the angular velocity must perfectly automatically accelerate. Whether it is the imperceptible recoil of the Earth against a falling object, or the accelerating spin of a skater collapsing their geometry, the universe continuously balances its books. Momentum is strictly conserved.